Hi there. Hope you're having an awesome day today. Today is another great day for chemistry. So let's get going. Today we're going to talk about the periodic table a little bit more, and we're going to tie in what we learned last chapter with electron configuration to the periodic table today. So we're going to just uncover a little bit more of the really cool connections that the periodic table has to how the electrons are arranged in around the atom. So electron configuration of the periodic table, section 5.2. Our objectives today: make sure that we're distinguishing between groups and periods. We got that down, right? Locate the common families. So we're going to give you some names for these families now of the periodic table. Determine the period of an element given its electron configuration. So I can give you the electron configuration, 1s2, 2s2, 2p4, and you're going to be able to tell me which element it is. Woo! That's cool. All right. Identify which block of the periodic table an element is based upon its electron configuration. So if I were to have told you that 2p4 thing and finished off with 2p4, you'd also be able to tell me the period. Okay, so you'll be able to tell me the group or family, and then you'll be able to tell me the period, both. All right. So your criteria for success: given an element, you're going to be able to tell whether it's a metal, non-metal, metalloid, and list the group and period. Then you're going to show the location, describe the properties of the alkaline metals, alkaline earth metals, transition metals, halogens, and noble gases. We've got a few different parts of the periodic table that we're going to make sure that we can identify. Let's talk about the organization of the periodic table. There are different ways to organize or break the table down. One of them is by group, right? So another word for group is the family, okay, or the columns, right? So we've got family, or we have the columns that you can talk about there as well. So we can talk about the organization based upon the families, and we have to remember that these have similar properties, and that's why we call it family, right? People in a family have some similar properties, the way they look or some characteristics they have, some of their interests. Same thing with elements, okay? And the reason that they have similar characteristics is because of the same number of valence electrons. Okay, so the valence electrons determines those similar properties, the reactivity, for instance. We'll talk more about that, right? Electron configuration has to do with reactivity. So, for instance, lithium and sodium are in group. Okay, boom, you should be able to look at that, pause it if you need to, go answer and come back. They're in group 1. And they have how many valence electrons? Well, they have 1 valence electron. And they have an outer electron configuration of, so their outer configuration, the last things that they have are always going to be an S1, okay? So for instance, lithium would have the configuration 2s1, sodium would have the configuration 3s1, okay? So they're going to have that S1 as their last configuration. S sublevel, 1 electron, okay? So that's basically what they're saying. It's in that group. The S sublevel is going to be in that first group, and they're going to have 1 valence electron on the outside. So that little electron configuration tells us a little story, tells us some information. Love it when the information is hidden in things. All right, our periods. Periods, remember, are going to be in the rows, right? And we're going to show you in a picture here how those orbitals that we talked about before, the different shapes that we have for our electrons around the atom, that they are actually broken down into groups on the periodic table. So that S sublevel right here, just 2 columns. The P sublevel, those 6 columns. The D sublevel, those 10 columns. And then the F sublevel, it's going to be those 14 columns. I forgot what number I had in my head there. All right, so S, P, D, and F. So I want you to make sure that you can identify those different ones, all right? S, P, D, and F. Now you'll notice that the hydrogen in helium, okay, helium is right there, and it kind of could belong right there. It's purple, right? It's in the S sublevel, and it kind of could fit here based upon some of its characteristics, but in the other ways, the hydrogen can kind of fit over here based upon its characteristics. So those two kind of bounce back and forth across the periodic table if you want to kind of imagine it that way. All right, so where are our metals? Where are our non-metals? Where our metals are pretty much everything on the periodic table. Okay, pretty much all that stuff is all metals, right? Lots and lots and lots of metals. I don't like that marker. Time to get rid of that marker. All right. Now, where are your nonmetals? Your nonmetals are going to be over here, right? We've learned about where our nonmetals are. We've got a little bit of a stair-step ladder that's going to go through and tell us our metalloids too. All right, so you've got the nonmetals, and then you've got your metalloids, which are going to be along this stair-step line here as well. Okay, so you've got boron, you've got silicon, you've got germanium, you've got arsenic. These are our metalloids, right? Antimony, tellurium, and polonium. Okay. Astatine is actually considered a nonmetal, if I remember correctly. So these are your metalloids, and then you've got nonmetals, metals everywhere else. Okay. All right. So that zigzag line is what's going to separate those metalloids. What element is? Let's see if you can figure this out. In group 2, period 3. Pause it and practice, and you're back. Group 2, it's the second column, period 3. 1, 2, 3. Okay? So group 2, period 3. Which one intersects that? That one right there, right? And so that's going to be magnesium, right? So that should be magnesium, element number 12, atomic number 12. Okay. What's the only nonmetal in group 14? So I got to go count over to group 14. And here's group 14. Okay, we count 1, 2, 3, 4, 5 all the way across. And these are metalloids. These are metals. So the only nonmetal that they're asking about is that one right there. Okay, and so what's right next to boron? Carbon. Carbon's the only nonmetal in group 14. What's at the beginning of the D block in period 5? All right, period 5. So there's 4, there's 5. The beginning of the D block. This is the D block in period 5. And so we got to identify that element, and that is our good friend yttrium. Little Y there, right? Why is it called yttrium? Well, because it's one of the many elements that was named after Ytterby, Sweden. I think it's in Sweden. There's like 6 different elements that were discovered in that, like with this tiny little village town where it's got this really weird place where aliens came down and gave them. No, I'm just kidding. But it has this really strange phenomena. Like most of these particular 6 elements on Earth are found in this one little village. And it's just kind of weird. There are other locations for it, though. All right. No, it has nothing to do with aliens. Okay, so you know, if we were in class, if we were in seat, you guys would be doing a periodic table. You'd be labeling it and coloring it. You'd be using it. So you can print one of these out and label it and color it if you want. You can use the color one that I've given you, however you want. But just make sure you're getting familiar with these different groups and that you know where everything is. The alkali metals, that's the first column. Okay, the very first column on that periodic table is the alkali metals. We're looking at that one right there, alkali metals, starting with hydrogen at the top. Now, hydrogen is not a metal, it's a non-metal, but it's at the top of the alkali metal group. We wouldn't call it an alkali metal, though, okay? These guys in this first column are very reactive. That's one of their properties. The alkaline earth metals are not as reactive, but they're still reactive, okay? And then you get to the transition metals. And again, these things are all going to have, and they're right here in that D block, they're all going to have similar properties. It's the ones that are blue here, okay? Those blue ones, they're all going to have pretty similar properties. That's that D block. They're going to be metallic. They're going to be dense. They're going to be solid, except for mercury, right? Typical metallic properties. And then you have your post-transition metals. Now, post-transition metals is a way of talking about this little inner group, okay? So we call them the lanthanides and the actinides. And I'm going to try to isolate just those two there. It's that bottom section right there, okay? This is the post-transition or the inter-transition metals. Oh, I am such an idiot. No, this is, I have inter-transition metals in my head, and I'm reading post-transition metals. Post-transition metals, these little guys right here, okay? The ones that are after the transition metals. and they're in that little space there underneath where the probably might not even be able to see that. They're in that little space there after the transition metals, and they're going to be the ones that are underneath like the metalloids, right? Sorry, idiot moment there. It's okay. We're all allowed to have them. All right, and then you have the halogens, which are the 17th column, okay? The 17th column is going to be this last one here, not the last one, but the second to last one here, the penultimate column, and those are the halogens, okay? Group 17. On this periodic table, it's this one here. Now you're like, why do you have two different periodic tables, Powers? What is up here? Well, I just want you to see that this green section on this other periodic table, that's the F subgroup. This is the way the periodic table, really could be shown, except that they save space on the walls. And so by putting it underneath, then they're saving space. But you can see this little gap here is where this thing actually goes. And so on this periodic table, they're actually showing you, yes, here, it is actually there. And that's what we're about to get to here. We're almost there. Noble gases are unreactive. That's that last column. Okay, that's that final column. Noble gases, didn't even discover those things until after most all the other elements had been discovered. Didn't even know they existed, discovered them on the sun. Hydrogen's kind of, again, one of its own kind. It can be all the way over there, kind of like on the halogens, and it can be kind of with the alkali metals because it's got one valence electron, but that's like the alkali metals, but it also has just one more that it needs to get a complete shell in that S sublevel, and that's a lot like the, having one more is a lot like the halogens, and so it just needs one more, and that's like a halogen, but it has one, and that's like an alkali metal, so it's kind of unique. All right, there we go. Lanthanides and actinides, called the rare earth or intertransition metals. Okay, now we're getting on to some truth here. And so that's what I was trying to show you here, right? The intertransition metals are those little guys there, that F sublevel, and those are the ones that have those really crazy orbital shapes. And many of these, if you look at certain periodic tables, you're going to see a good chunk of these are actually they'll have like a clear outline. A lot of them are radioactive, okay? Which, well, a lot of them are radioactive, but if they have a clear outline, they're actually man-made. If you look at the periodic table when you come into class, you'll see it has one where they're clear outlines. The clear outline elements are ones that were man-made, so they're not found in nature anywhere. We have ways that we can number them. We can number them 1 to 18, which is basically the only way that we do it nowadays. They do have another numbering system, but I learned when I was in high school, that's the way we did it, but then they got smart and said, hey, it's a lot easier to do 1 to 18. Yeah, it is. Okay, you can kind of see those different numbering systems here. It's goofy, don't worry about it. But anyway, if you wanted to color your periodic table, you can color it like this. If you want to hit pause, boom, you can do that, come back, and here we are. Now, those transition metals, like I said, that's in the D block, right? Less reactive than the alkali metals and the alkali earth metals. They are found in nature as pure elements, okay? For instance, we can find veins of gold and silver and platinum and copper, things like that, right? They form lots of colored compounds. And yeah, we already talked about the fact that they're the D block elements. Okay, so let's talk about these electron configurations, because I want you to see that the electron configuration can be deduced from the periodic table if we just look at the columns and the rows, right? So we know that these are S block elements. We know that these are the P block elements. We know that these are the D block elements and that these are the F block elements. And so if we wanted to talk about a certain electron configuration, a certain electron notation, we could just basically point to any element in this whole periodic table and you can tell us the configuration. Now, one thing that's kind of tricky about this, you'll notice we have period 1, 2, and 3, and then we have period 4. But look at this. This D block is actually a 3D. That says 3D there. Now, you just have to remember that the D block has 1 minus of the energy level, okay? So if my energy level is 4, my D block is 1 minus that, okay? And so 1 minus that, that minus 1. So it'd be 4 minus 1, so it'd be 3. My D block is 5 minus 1, it's actually 4, okay? So if my D block is in the sixth row or sixth period, then my D block is going to be 5. Now, notice that our inner transition elements are actually stuck with 2 that you subtract from. They're minus 2, okay? So for instance, if I count down here, period 1, period 2, period 3, period 4, period 5, period 6. In period 6, I go to my F block that is 4F. So this is 4F, 6S, 4F, 5D. Okay, so the D's, you subtract 1 from the energy level, and then the F's, you subtract 2 from the energy level to figure out what they are. Now that kind of seems weird, but the reason that we do that, again, is because it's really easy to do an electron configuration if we understand the filling order. This periodic table has been arranged essentially in the way that the electrons are going to fill their energy levels, okay? And so if you want to see how the electrons fill their energy levels, you just read the periodic table left to right, top to bottom. And it goes like this: 1s, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, etc., right? 2p6, 3s1, 2, 3p, 1 through 6, 4s, 1 and 2, 3d, 1 through 10, 4p, 1 through 6, 5s, 1 and 2. Okay, now we go 4D, 1 through 10, 5P, 1 through 6, and now we hit 6S. Before we jump down into the D's, we will start hitting our F's. Okay, so we go 6S, 1 and 2. There's actually a little 5D1 that happens there. We won't talk about that right now. And then you go to 4F's, 1 through 14, then you kick back 5D's, 1 through 10, and then 6 P's, 1 through 6. So anything that you do, remember that little mnemonic device that we had where we had the angles and how we figured out how to name them? Again, it's all on the periodic table. So we can just choose any element. Let's say I choose this element here, okay? And I want to know the electron configuration. Well, let's write it out. Where am I going to write it out? Not much room here. 1s2, 2s2, 2p6. Where am I so far? 1s2, 2s2, 2p6, 3s2, 3p. There's 6 of those. 6. 4s2. Just going across. This is not 4p, this is 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d, 10. 4p, 6. Keep going. 5s2. And then 4d, 1, 2, 3, 4, 5, 6, 7. 4d7. And that would be my electron configuration. Okay. Now, from that, I can tell you how many valence electrons there are. Remember, the number of valence electrons is the number of electrons in the outermost energy level. So 5s2, there's 2 electrons in my outermost energy level here. So my valence electrons is 2. Okay. So, yeah, if you can take any element from the periodic table, you can tell me what the electron configuration is if you just kind of go left to right and start numbering them as you go. It's pretty simple. All right, questions? I'm sure you've got plenty, okay? Make sure you ask those questions as you come into class so I can help you out. So, for instance, we would want you to write the electron configuration for Se, all right? So practice it yourself. Find Se, that's selenium. It's number 34 in the periodic table. Write the electron configuration for it. I can look at it right now, and I can tell you that the last 2, okay, the last little thing that you're going to see there is going to be 4p4, okay? You can look at it immediately. It's in the P sublevel. It's in the 4th energy level. And it's 4 across. Okay, so if we look at that, we find selenium, and it's right here. Okay, selenium is number 34. It's right there, and I can say, oh look, it's in the P sublevel in the 4th energy level. This is 4, right? On this period, it's the 4th period, and it's in the 4th period in the P sublevel, and then it is 1, 2, 3, 4 spots over. Okay, and so I'm going to say, oh, well, it's 4 spots over in the P sublevel, so it's 4p4, 4th energy level, P sublevel, 4 spots over. That's what that's all about. Okay? Cool, huh? Yeah. All right. Now, you should be able to fill out this table, okay? Now that you have all this information in your brains, you should be able to create this table in your notes. Talk to me about reactivity, the ionic charge, and its properties. You're like, Powers, we haven't talked about the ionic charge. You're wearing that little cation shirt, but you haven't really talked about the ionic charge. The ionic charge is the charge it's likely to form when it forms an ion, okay? So, for instance, we were just looking at selenium. Let's go back to that real quick. If selenium is right here, then what is it going to want to do? It's going to want to get a full octet. Remember, when ions form, they try to get the full octet of electrons. And so it wants to, right now it's got 4p4. It's got 4 electrons in the p sublevel. It also had 4 electrons in the s sublevel. So it was 4s2, 3d10, 4p4. So its number of valence electrons had to do with the last outermost energy level. So it's got 6 electrons in its outermost energy level. 2 plus 4 is 6. And how many do these atoms want? They want to have 8. So everything in this block right here wants to get 2 more to get to 8. And so in this case, all of these guys are going to want to form a -2 ion. These guys want 1 more, so they form a -1 ion. These guys don't form ions, right? Because they're happy. They have a full octet. These guys form -3 ions. They want 3 more to get to 8. Now these guys are right at that place where you could form 4, or you could like give 4 or take 4, and you're going to basically be in the same boat. And so we usually don't ask you to figure those out because it can be a plus or -4 depending. But once you get over here to the 3rd block, then these guys are actually going to form a +3 ion, because it's easier to give away 3 electrons than it is to gain 5 electrons. These guys are going to form a +2 ion. These guys are going to form a +1 ion. Okay, so you can fill out that chart now that you know that. Those ions are important to remember. You're always trying to get to 8 total valence electrons. These guys have 1 valence electron, easy to get one and get rid of it, right? So for instance, if I'm sodium is 3s1, here's sodium, and I've got 1 little electron that I could get rid of to make a more complete energy level and make it look like neon. Okay, so if I get rid of 1 of my extra electrons and form a 1+ charge, then now my electron configuration is going to be the same as neon. And it's actually a more stable, lower potential energy state atom at that point. Okay, the reason that these atoms are going to give away electrons or gain electrons is so they can get to a more stable potential energy state. And so if sodium can give away electron, it's going to do it because it gives it to a more stable state. Fluorine is going to want to get one because it gets it to a more stable state. Okay. All right, so you should be able to fill out that chart now and tell me some of these properties. Okay. So pause it and come back. And we're back. All right, so our reactivity, very reactive, typical ionic charge, +1, properties. Okay, these are metals, and they're actually usually soft metals, but they're still going to be, able to conduct electricity and things like that. So typical metal properties, but those alkali metals oftentimes are actually soft. You can cut them with a knife, a lot of them. Alkali earth metals, not as reactive. So they're still reactive, but not very reactive, right? So yeah, moderately reactive or somewhat, or they're reactive. I don't know what word I like in that one. They're reactive, just not very reactive, not as reactive. +2 alkali earth metals are going to have a +2 charge, and again, they're going to be metal. And they're called alkali earth metals because these particular elements, when they are burned, they don't, when they're put in fire, they don't actually burn. So they kind of have like the earth property, earth, fire, wind, and water. They actually kind of stay in a form that doesn't disappear. So for instance, you put calcium in there, you stick some bones in the fire, and the bones are going to, not, the calcium's still going to end up being in there. Yeah. explanations are subpar today. Okay, halogens, these are actually very reactive as well, okay? So they're very reactive, but they're very reactive on the other side of the scale. These are going to want to give away an electron. These are going to want to take an electron, and so these will react with these really well, right? And then properties, a lot of these, again, these are nonmetals, right? And these are a lot of times going to be gases, okay? Some of them are poisonous. Chlorine and fluorine are going to be poisonous. Noble gases, those are non-reactive, okay? May not know how to say semi-reactive, but I know how to say something non-reactive. They're charged. They don't form an ionic charge. So they're not gonna have a value there. You can say not applicable or not forming an ion. And then the non-metal gases, these are also non-metal gases, right? That's why they're called noble gases. And so these do have properties that are just not reactive. Now, scientists have been able to force these things into reactions under really high temperatures and high pressures, but for the most part, you know, they don't, and definitely not naturally that we typically find them reacting. Suppose there's some natural phenomena like in lightning or something that would create some of those possible compounds as well, but typically man-made. All right, so our intertransition metals, again, radioactive, many of them are man-made. The F block elements, and there are two elements, lanthanum and actinium. Okay, lanthanum is right there, number 57. Actinium is number 89. These are the two elements that kind of start the lanthanides and the actinides. That's why they're called lanthanides and actinides, is because of lanthanum and actinium. Okay, and this periodic table is actually kind of cool because it actually tells you the electron configuration, and you know the lanthanum gets the electron first, and then it goes to cerium. And so if you look at this periodic table, you can see that we have lanthanum is actually in the D sublevel. It's kind of hard to see, but this one's color coded blue, and so you can kind of see that the lanthanum is actually the blue. If you come over here, then it's weird because you've got 14 of these, and it actually throws and puts an electron. It goes 6s2 and then does 5d1, so it pops one over here into 5d, and then on the next one it starts going and it starts doing 6s2, 5d1, 4f1. So this cerium is the first 4f1. It's a little bit confusing, but you can look into that more. It hurts my head when I talk about it. I'm not going to talk about it anymore. I don't need to hurt my head. You don't need to hurt your head right now. We'll hurt it later. All right, so it's not testable, okay? Don't worry about it. All right, so objectives review. Distinguish between the groups and the periods. Yeah, we know. Groups are up and down. Periods are horizontal, right? Locate the common families. Now we know things like the alkali metals, the alkali earth metals, the halogens, the noble gases. Determine the period of an element given its electron configuration. All right, so I can say, you know, 3s2, and you can be like, oh, that's third period, right? Because it's 3s2, 3. All right, and then identify which of the periodic table of the elements is based upon its electron configuration. So which block of the periodic table would you find if I said, you know, 5d2? You know, oh, well, that's got to be, you know, if it finishes at 5d2, it's got to be in the D block elements, okay? All right. Did we do it? Oh, yeah, criteria, success, review. Yeah, can we explain how Mendeleev's organized the periodic table? That was last time. Bad one. All right, next one. Given an element, can you tell whether it's a metal, non-metal, or metalloid? And its group and period? Yeah, we can totally tell where these things are now. And can we show the location, describe properties of things like alkaline metals, alkaline earth metals, transition metals, halogens, noble gases? Yeah, you guys are smart. You can do that. All right, my brain is fried. I don't know what day it is when you're watching this, but this is Friday, and this is subpar lecturing on my part. But still, I'm sure you learned a bunch, because a lot of what I said, almost 100% of what I said was totally on point. Just a little bit of blabbering there, but you know what? It's good for you to see me blabber because I'm human. I know you thought I was like some sort of like, yeah, but no, I'm human, fallible. I have my days, good and bad, and today's just not a great lecture day. But I love you, and I love teaching. I hope you guys love chemistry as much as I do, or at least will someday, if you don't yet. And yeah, go hug a friend virtually. Don't touch them unless they're your family members or you're with them all the time. Don't let that COVID spread. I'm going to blabber on for another 10 minutes. No, I'm not. Bye. Have a good day. God bless you.